Section 8.1 is confidence intervals for a population mean when the population standard deviation is known. This is what we're going to do only if we know the population standard deviation. Keep in mind that it's really rare to know the population standard deviation. In section 8.2, we're going to see what to do when we're finding a confidence interval for a population mean when the standard deviation is unknown. There's 5 objectives in this section. Let's get started with objective 1. Objective 1 is to construct and interpret confidence intervals for a population mean when a population standard deviation is known. Keep in mind, this is what we're trying to approximate. Remember, the population mean is mu, x bar is the sample mean. This is your population parameter and your sample statistic. A simple random sample of 100 fourth graders is selected to take part in a new experimental approach to teaching reading. At the end of the program, the students are given a standardized reading test. On the basis of past results, it is known that the scores of the test have a population standard deviation of 15. The sample mean scores for the 100 students was 67.3. The administrators want to estimate what the mean score would be if the entire population of fourth graders in the district had enrolled in the program. The best estimate for the population mean is the sample mean. The sample mean is what we call a point estimate because it's a single number, so it's a single point. It's very unlikely that 67.3 is the exact score that the population would have if all the fourth graders took the reading test. Therefore, in order for the estimate to be useful, we must describe how close it is likely to be. For example, if we think that it could be off by 10 points, we would estimate the population mean with the interval 57.3 to 77.3, which could be written like this. This plus or minus 10% is what we call our margin of error. Whenever you're finding a confidence interval, what you're finding is a range of numerical values that you think the population parameter could be one of those numbers within that range. How we find a confidence interval is we take our point estimate plus or minus some margin of error. Tonight I'm going to show you how to find that margin of error. The point estimate when you're estimating a population mean is just x bar. So this would be x bar plus or minus some margin of error. What you're going to see tonight is that that margin of error is going to be some critical value times the standard error, which is the population standard deviation divided by the square root of n. This was our standard error or our standard deviation from the central limit theorem. This critical value is determined by what your confidence level is. So for a 95% confidence interval, we need to determine how large to make the margin of error so that the interval is likely to contain the population mean. To do this, we use the sampling distribution of x bar. This is the distribution from the central limit theorem. Because the sample size is large, we had a sample of 100 students. The central limit theorem tells us that the sampling distribution is approximately normal with a mean of mu and a standard error of sigma divided by the square root of n. For the teaching reading example, the standard error would be 15 divided by the square root of 100, or 1.5. So now we construct a 95% confidence interval for mu. We begin with the normal curve and then find the z-score that bounds the middle 95%. When we do that, we come up with these z-scores of negative 1.96 and positive 1.96. The one that's on the positive side is what we call our critical value. And do you remember how we would get this number on the calculator if this was the area that I wanted in the middle? Inverse norm, not 0.95, it's 1 minus 0.025. Well, that's 1 minus alpha over 2, and the mean is 0 and the standard deviation is 1. Because I want a 95% confidence interval, alpha here would be equal to 0.05. That alpha region has to be split evenly over the two tails since I wanted the middle area to be 0.95. That's why this area is 0.025, because half of 0.05 is 0.025. Alpha is the 5% that we're not going to be confident in. So for a 95% confidence interval, our alpha is going to be the remaining 5% that keeps us from being 100% confident. The area of 0.95 is the middle area. When I'm talking about alpha, I'm talking about what part is left over in either of the two tails. So that 5% gets split evenly over the two tails. That's why for my area in the inverse norm, I have alpha divided by 2. Because alpha is 0.05, this area right here would be half of that. And that gives me this critical value right here on the upper end. Let's look at it on our calculator. So I would go to inverse norm. My area would be 1 minus 0.05 divided by 2. The mean is 0, the standard deviation is 1, and when I hit enter, that gives me my critical value of 1.96. Now to calculate your margin of error, you just take your critical value times your standard deviation divided by the square root of n, and that gives us 2.94. So our margin of error is 2.94. To get the bounds on this confidence interval, I would take x bar minus 2.94 and x bar plus 2.94. Well, x bar we said in the problem was 67.3. So when I do 67.3 minus 2.94, I get 64.36. And when I do 67.3 plus 2.94, I get 70.24. What that means is, based on a sample of 100 fourth graders using the new approach to teach reading, a 95% confidence interval for the mean score is going to be between 64.36 and 70.24. What we would say is that we are 95% sure that the average reading score will be between 64.4 and 70.2. This formula gives us the bounds for our confidence interval. This formula right here, x bar plus or minus the critical value times your standard error.
Where did you get the 1.5 that you're multiplying by?
Sigma divided by the square root of n, and we were told in the problem sigma was 15, the population standard deviation. There were 100 students, the square root of 100 is 10, 15 divided by 10 is 1.5. Now, based on the sample of the 100 fourth graders, this is our 95% confidence interval right here. So 95% is the confidence level for the confidence interval. It's our confidence in the process of actually capturing what that population mean is. Here's a graph that represents many different samples, and we use each one to construct a confidence interval. Then in the long run, the percentage of confidence intervals here, each one of these horizontal lines represents a different confidence interval. We would say in the long run that 95% of the time we expect this confidence interval to contain the true value of the population mean, even though we don't know what that population mean is. This vertical line represents the population mean. Each one of these blue lines would be a confidence interval. On this confidence interval, the true value of the mean is a little closer to the left. Over here, this confidence interval right here, the population parameter is a little closer to the right. Here, and here, I've completely missed the mark. Not every confidence interval will contain the true value of this population mean. Some of them are going to miss. Otherwise, I'd say I was 100% confident. A 95% confidence interval means that about 95% of the times that we do this process of taking a sample, calculating the mean, and then creating a confidence interval, 95% of the time I expect that confidence interval to actually contain the population parameter that I'm looking for. The confidence interval gives us a range of values that we can use to approximate the population parameter, whereas x bar is just a single numerical value. We're more likely to get a better idea of what the population mean is when we look at a confidence interval. A point estimate is a single number that's used to estimate a value of an unknown parameter. In this section and in the next, we're looking for an estimate on the mean. So our point estimate will be x bar. A confidence interval is a range of numerical values that we use to estimate that parameter. The confidence level is a percentage between 0 and 100% that measures the success rate of the method used to construct that confidence interval. We're not saying that 95% of the time the mean is in there. That 95% is not a probability. It's a level of confidence in the process. And as we go through tonight's lesson, hopefully you'll begin to understand that process a little better. I understand this is the first time you guys have seen this, and it's going to feel uncomfortable until we get more comfortable with the terminology and the process. I just gave you a quick run through of the process, a big overview of it. The margin of error is computed by multiplying the critical value by the standard error. For this problem, our critical value will be a z-score that's found by taking our alpha level. By the way, Alpha is going to be 1 minus our confidence level, written as a decimal. We take that alpha level and divide it by 2 then. So if I had a 95% confidence interval, this area right here in the middle would be 0.95. Alpha would be equal to 0.05, and alpha over 2 would be equal to 0.05 divided by 2, and that's 0.025. This critical value is found using inverse norm for a standard normal distribution. The margin of error is the critical value times our standard error, which is sigma divided by the square root of n. This is our margin of error. I'm using ME as my abbreviation for margin of error. How I get my confidence interval is x bar plus or minus my critical value times my standard error, sigma divided by the square root of n. This needs to be on your formula sheet. This is how we calculate the confidence interval. This is how we find alpha. This is our margin of error. And this is how we find that numerical value. Objective 2 is finding critical values for confidence intervals. Although 95% is the most commonly used confidence level, sometimes we will want to construct a confidence interval with a different level. We can construct a confidence interval with any confidence level between 0 and 100% by finding the appropriate critical value for that level. The critical values for several common confidence intervals are given below. The one that we use most often in social sciences is 95%. 99% is used a lot of times in medical research. And if you're doing a pilot study, sometimes you'll use 80% or even 90%. These are the most common confidence levels. Because these confidence levels are associated with z-scores, the z-scores don't change. So in theory, you could memorize this, but I'm more interested in, can you find the critical value? Because on your test, I'm not going to give you one of these common confidence levels. Of course not. I'm going to challenge you and see if you understand it. So don't fight it. You might as well learn it. So let's go through this example. We're told a large sample has a mean of 7.1 and a standard error of 2.3. You're given the complete standard error here. We're told to construct a 90% confidence interval for the population mean. Start with the formula for a confidence interval. That's x bar plus or minus z sub alpha over 2 times sigma divided by the square root of n. I know a number for x bar, don't I? 7.1. And I know a number for sigma divided by the square root of n, 2.3. This is the one that I've got to figure out, the critical value. Let's go through the process of finding the critical value. We start with the normal distribution. Because I want a 90% confidence interval, I know this area in the middle has to be 90%. What is alpha going to be? 10%. And that 10% is going to be split evenly over these two tails. So what will be the area in one of the tails? 0.05, not 0.5. 0.5 is a half. My critical value is this z-score associated with this area of 0.05 to the right. How do I find that critical value? Inverse norm, 1 minus 0.05, that's our alpha divided by 2, 0, and 1. And when you put that in your calculator, what do you get? 1.645. For a 90% confidence interval, our critical value is 1.645 because alpha was 0.10. If you put 0.10 divided by 2, then you'll get the right answer for 1 minus alpha over 2. If you put in the 0.05, you'll get the right answer. Watch. 1 minus 0.05 is the same thing as 1 minus 0.10 divided by 2 because 0.10 divided by 2 is 0.05. These are going to give you the exact same answer because 0.05 is 0.10 divided by 2. So that gives us our critical value. So to set up our confidence interval, we're going to look at 7.1 minus 1.645 times 2.3. This is going to be our lower bound. And 7.1 plus 1.645 times 2.3 will be our upper bound. So let's go to our calculators. So we do 7.1 minus 1.645 times 2.3. And rather than type everything in again, I'm going to hit second enter and then use these arrows here to move my cursor over to the minus and change that to a plus, and that gives me my upper bound. Because my data that they gave me was rounded to 1 decimal place, I'm going to round my answer to 1 decimal place. So what I would say here is that our population mean is going to be between 3.3 and 10.9. This would be my confidence interval if I'm rounding it to 1 decimal place, and I chose to round it to 1 decimal place because both my sample mean and my standard error were rounded to 1 decimal place. Do you see how it comes from this formula right here? X bar plus or minus the critical value times the standard error. Sometimes we may need to find a critical value for a confidence level that's not given in a table. To do this, it's useful to learn a notation for the z-score with a given area to its right. The notation z sub alpha refers to a z-score with an area of alpha to the right. The notation z sub alpha over 2 refers to a z-score with an area of alpha over 2 to the right. Alpha is equal to 1 minus your confidence level, written as a decimal. And whenever you determine alpha, 1 minus alpha, we take that area of alpha and we split it over the two tails evenly. That's why this area that's not shaded in is called alpha over 2. So in this example, I ask you to find the critical value z sub alpha over 2 for a 92% confidence interval. For a 92% confidence interval, what is alpha going to be equal to? 0.08. That means that alpha divided by 2 is 0.04. The way I would look at this in a picture is I would draw a normal curve. The area in the middle has got to be 92%. And then that 8% that's left over is split evenly over these two tails. So this area right here is 0.04. That's alpha divided by 2. My critical value I find by using inverse norm, 1 minus 0.04, 0 and 1. That's 1 minus alpha over 2. The mean is 0. The standard deviation is 1. So we go to our calculators. So we hit second vars number 3. Our area is now 1 minus 0.04. If you want to do 0.08 divided by 2, you can. The mean is 0, the standard deviation is 1, and we get 1.75. Just to show you that it doesn't make a difference, if I did 1 minus 0.08 divided by 2 for my area, I get the exact same value. So this would be 1.75. Notice, this value we said was alpha divided by 2, but if you want to type it in as alpha divided by 2, you're going to get the same answer, 1.75. It doesn't change the answer. It doesn't matter how you type it in. I'm giving you options. The method that we described for confidence intervals requires us to assume that the population standard deviation is known, and you have to be estimating a population mean. In practice, though, sigma is not known. We do have some distributions where we do know what the population standard deviation is. For example, IQ scores we know are normally distributed with a mean of 100 and a standard deviation of 15. We know that because we've been studying IQ scores for decades. We have a lot of data on those. So we make the assumption that we know what sigma is because it allows us to use the familiar normal distribution. In the next section, we're going to look at what to do if sigma is unknown. Other assumptions that we have to check is that we have a simple random sample. If you don't have a random sample, that means that you've got bias in your data and there's no amount of statistical torturing that can redeem poorly collected data. So you've got to have a simple random sample. Then you've also got to know that your sample size is sufficiently large or the population is approximately normal. This is an either or. Either the sample size is large or the original population is normally distributed. So in this problem, we want to construct a confidence interval. A machine that fills cereal boxes is supposed to put 20 ounces of cereal in each box. A simple random sample of 6 boxes is found to contain a sample mean of 20.25 ounces of cereal. It's known from past experience that fill weights are normally distributed. That means that this condition up here is satisfied. And we needed to know that because our sample size is small. N is equal to 6 here. We have these 6 boxes of cereal. Because our sample size is small, we have to know the population is normally distributed, and it is. So the standard deviation is 0.2 ounces, so I know sigma. Construct a 90% confidence interval for the mean fill weight. By the way, the sample mean is 20.25. For a 90% confidence interval, CI I use to abbreviate confidence interval, what is alpha going to be? 0.10. So what is alpha over 2 going to be? And what did we just find that critical value to be for a 90% confidence interval? 1.645. So now we're ready to construct our confidence interval. Our confidence interval is going to be x bar plus or minus z sub alpha over 2 times sigma over the square root of n. For this problem, x bar we were told is 20.25 plus or minus 1.645 times what is sigma? 0.2 divided by the square root of what is n? 6. So we go to our calculator. On our calculator, we're going to hit 20.25 minus 1.645 times 0.2 divided by the square root of 6. That'll give us our lower bound, and change that minus to a plus to get your upper bound. And that means that our confidence interval on the mean will go from 20.12 to 20.38. So we're 90% sure that the average weight of cereal in the box is between 20.2 and 20.38 ounces. So do you think the manufacturer is safe in saying that there's 20 ounces of cereal in that box? Yeah, because both the lower bound and the upper bound on our confidence interval are bigger than 20. That's how we use the confidence interval. If this would have been a number less than 20, then the manufacturer might have gotten in trouble by saying that there's 20 ounces of cereal in the box, because he's shortchanging the public. Now, there is a way to do the confidence intervals on the calculator so that you don't have to know this formula right here. However, I wanted to teach it to you first using the formula so you can see what all these different component parts are. Now I'm going to show you how to do this on the calculator. We're going to hit Stat, go over to Tests, and what we're finding is a Z interval. So let's rework this problem using the calculator. On our calculator, we're going to hit Stat, go over to Tests, and we go down to Z interval. Let's do that now. Stat, Tests, Z interval on my calculator is number 7. Then it's going to ask you for your input. Do you have a list of raw data or do you have summary statistics? We don't have raw data. We have summary statistics. The first thing it's going to ask for is the population standard deviation. That was 0.2. The next thing it's going to ask for is the mean. The mean weight of the cereal we said from our sample is 20.25. Our sample size was 6. And our confidence level was 90%, so we're going to put our C level at 0.9, and then we hit enter. This screen right here gives us our output. Notice we get the same answer. It goes from 20.12 to 20.38. Stat, test, go down to Z interval. Interval because we're finding a confidence interval. There's also something on there called a Z test. That's not what we're doing. Objective 3 is to describe the relationship between the confidence level and the margin of error. Let's talk about confidence versus margins of error. If we want to be more confident that our interval contains a true value, then we have to increase the critical value, which increases the margin of error. There is a trade-off. We would rather have a higher level of confidence than a lower level, but we would also rather have a smaller margin of error than a larger one. For example, if I wanted to be 100% confident on today's high temperature, I want to know how I'm going to dress today. Well, all I got to do is make that confidence interval or that margin of error really big. You know, if the weatherman came on today and said today's high is going to be between 82 and 86, I would know how to dress. But if he told me he's only 90% confident that today's high is between those two values, he may miss the mark. It may be warmer, it may be cooler. But if I say, weatherman, I want you to be 100% confident on today's high temperature, all he's got to do is say, okay, today's high temperature is going to be somewhere between -10 and 110. That doesn't help me know how to dress, but he's 100% confident in his answer. Same thing happens with confidence intervals. If we have a lower level of confidence, we have these little bitty narrow confidence intervals, which helps us zero in on a number. If we increase our level of confidence, we end up with these really long confidence intervals that may not be as meaningful or helpful to us. That's why in social sciences, we kind of take the middle ground and we say that 95% would be the level of confidence that we would use. So if you're doing any sort of sociology or education or any kind of social science research, that's why we use 95% levels of confidence in a lot of things that we do. But if you're doing medical research, you may need that higher degree of confidence. But just know that it's going to lengthen your confidence interval. The diagram presents 100 different 95% confidence intervals. When we construct a confidence interval with a level of 95%, we're getting a look at just one of these confidence intervals. We don't get to see any of the other confidence intervals, nor do we get to see the vertical line that indicates where the true value of the mean is. We cannot be sure whether we got one of the confidence intervals that covers the mean, which there's a whole bunch of them, or if we're unlucky enough to get one of these unsuccessful ones that totally misses the mean. We hope we get one that actually contains the mean for the population, but we might end up with one of these. That's why when you're doing research, you generally want to pull multiple samples and calculate different confidence intervals. What we do know is that our confidence interval was constructed by a method that succeeds 95% of the time. The confidence level describes the success rate of the method that we used to construct the confidence interval, not the success of any one particular interval. Objective 4 is to find the sample size necessary to obtain a confidence interval of a given width. You can predetermine what you want your width to be. Remember, I said that we find our confidence interval by looking at this. This product right here is our margin of error. One way to make that margin of error smaller is to decrease your confidence. Another way to make it smaller is to make this number smaller, and the way to make this number smaller is to increase your sample size. So if you want to hold your degree of confidence the same, the only way to get your margin of error smaller is to increase the sample size. So we can make the margin of error smaller if we're willing to reduce our level of confidence, but we can also reduce the margin of error by increasing the sample size. If we let M represent our margin of error, then we find that by looking at this product. It's what I just wrote down up here. Using algebra, we could solve this equation for n, and we end up with this equation. Put this equation in your notes, on your note sheet, because I'm not going to go through the algebra that we do to solve this. I don't want to confuse you with a bunch of algebra right now. I want you to just write this down. And this formula we can use to represent the minimum, to find the minimum sample size needed to achieve the desired margin of error. If the value of n is given by the formula is not a whole number, we're always going to round it up to the nearest whole number, no matter what it is. By rounding up, we can be sure that the margin of error is no greater than what we said we wanted. In this problem, we're told that scientists want to estimate the mean weight of mice after they have been fed a special diet. From previous studies, it's known that the weight is normally distributed, so I can use the normal distribution in the z-scores, with a standard deviation of 3 grams, so I know that sigma is equal to 3. How many mice must be weighed so that a 95% confidence interval will have a margin of error of 0.5 grams? Because I have a 95% confidence interval, z sub alpha over 2 will be equal to 1.96. We've already gone over how we found that critical value for this level of confidence. Using this formula now, n equals z sub alpha over 2 times sigma divided by our margin of error squared, I just drop in my numbers and then go to my calculator. So this is going to be 1.96 times 3 divided by 0.5 quantity squared. So we do 1.96 times 3 divided by 0.5, close parentheses, squared, and we get 138.28. So how many mice do we have to weigh? 139, because we round up to the next whole number. This is a different kind of rounding. Whenever you're finding the sample size, it's better to err on the side of caution and survey too many than too few. So we round up to the next whole number. And there it is written out all nice and pretty as well. Objective 5 is to distinguish between confidence and probability. Suppose that a 90% confidence interval for the mean weight of cereal boxes was computed, and this is actually what we computed. It is tempting to say that the probability is 90% that the population mean is somewhere between these two values. The term probability refers to random events which can come out differently when experiments are repeated. The numbers that we have on these bounds right here are fixed. They're not random. So the population mean is also fixed. This number that we're trying to estimate is also fixed, even if we don't know what it is. So the population mean is either going to be between this 20.12 and 20.38, or it's not. Therefore, we say we have 90% confidence that the population mean is in this interval, not that the population mean is one of those numbers. On the other hand, let's say that we are discussing a method used to construct a 90% confidence interval. The method will succeed in covering the population mean 90% of the time and fail the other 10% of the time. Therefore, it's correct to say that the method for constructing a 90% confidence interval has a probability of 90% of covering the population mean. This is a subtle but important difference. That 90% is our level of confidence in the process. We're saying 90% of the time we expect the population mean to be in there. And this summarizes everything that we've gone over in this section, and it's a lot. We'll hit it again in the next section and add something slightly different to it.